The International Space Station support laboratories where research in a range of scientific disciplines is conducted and is also a stable platform orbiting the Earth that supports a number of instruments that are looking down and gathering data about the planet and its systems. One new such instrument is scheduled to fly on the station later this year on a Dragon cargo ship. Dr. Joseph Zawodny at the Langley Research Center is the project scientist for the Stratospheric aerosol and gas experiment known as SAGE-3, and he recently talked with Langley's Kristen DeMatteo about what SAGE will be looking for.
Well, we're primarily an ozone and aerosol measuring system. The SAGE series, SAGE-3 is the third in the series, has been going on for a number of years. Over 40 years now. And the data is vital for measuring ozone, seeing how it's changing with time, and also aerosols, which I'll get into in a little bit, but they're important for climate.
Can you tell me a little bit about what efforts this project has grown from?
So as I said, this started almost 41 years ago with this little device. This is the Stratospheric Aerosol Measurement, SAM, and it flew on Apollo-Soyuz in the summer of 1975. Very simple little instrument, a diode at the end of this tube is aimed at the sun, lined up with the sight here. This was just clipped into the window of the Apollo spacecraft. They aimed it at the sun and let the spacecraft be our platform. It then watched the sunset, and what happens as that happens, sunlight is attenuated by the Earth's atmosphere, aerosols in particular. This was a one-channel instrument, made a single measurement at one micron in the infrared. Quickly after that followed SAM-2, which was on its own spacecraft. It lasted for over 16 years. Shortly thereafter, SAGE-1 was flown. That had several channels. It measured not only the aerosol at 1 micron, but it also measured ozone for the first time in occultation. That lasted 3 years. Spacecraft battery systems failed on that. Then in '84, we launched SAGE-2, which is probably our best known measurement system. It lasted 21 years. Fabulous data set. Important period too, because during that time ozone was first seen to be declining in the stratosphere, upper stratosphere. So the ozone layer is primarily in the stratosphere. And the chlorine compounds, freons in particular, were causing the destruction of ozone in the stratosphere. And we saw that happening, and by the mid-'80s, 1980s, the community had come along and noticed that the ozone was declining, started to take action, trying to figure out exactly what was happening. Turned out pretty clearly from SAGE data and SBUV data, another NASA satellite system that measures ozone. The pattern was such that we knew it was chlorine. Montreal Protocol was written up, signed by virtually every country on the planet, outlawing the use of freons. And later in the 21-year mission lifetime of SAGE-2, the first evidence that the chlorine decreases were actually being seen in the ozone were found. So it was a nice long mission. Near the end of that time, we started to work on SAGE-3. We've built 3 of those. The first one was flown in 2000 on a Russian meteor, lasted 5 years. And now we're on the second SAGE-3, and it was always designed to go on space station.
So this next piece of hardware, SAGE-3, is scheduled to fly later this year. Can you tell me a little bit more about the hardware and where it's going to go on the space station?
Yeah, the space station's an interesting place. There's lots of places to mount things. We're going out near the end of one of the arms on a place called EOC-4. Our payload comes up on the Dragon trunk in 2 pieces. This is the first of the pieces. It's a nadir viewing platform, and all it does is it replicates an interface that's vertical relative to the Earth and provides one that's horizontal. That's why it's called nadir viewing. This flat plate faces down towards the Earth. The second piece will also come up on the same flight, and the robotic system will install this first. This will be riding piggyback, and then it'll take this and install it like that. And then this completed assembly is our hardware. It's about 750 pounds, if I recall correctly. The SAGE instrument itself sits here, and this allows us, in this orientation, we can see virtually 360 degrees to the horizon, the limb of the Earth. We're looking at the thin layer of air that you can see off at the horizon. And from orbit, the instrument will rotate in azimuth to find the sun, and then there's a scan mirror in there which scans the field of view across the sun up and down. So we're making measurements of the solar brightness, the limb darkening curve. We look at it above the atmosphere, and then as the sun sets, we watch that light decrease due to scattering, absorption in the atmosphere. And we're measuring the spectrum from 290 nanometers past 1 micron, and then we have another channel, single channel at 1550 nanometers. And from that, we measure a number of things. We see the spectral fingerprints of gases like ozone, nitrogen dioxide, water vapor, oxygen. We measure temperature and pressure from that, a few other trace species. And then the broadband residual from all of that is due to aerosol.
How is the data that SAGE 3 is going to contribute to our understanding of the atmosphere and how we can better protect it?
So since the Montreal Protocol was enacted and apparently was very successful, we're expecting ozone to recover. It hit its minimum value in the late 90s. There's no real clear signal yet, despite it being 15 years or more since that onset of recovery. And it's just because the recovery is very slow. And you need a very precise measurement in order to see such a small change. And that's where occultation is ideal. The instrument effectively can degrade with time, but because it makes its measurement of the sun right before or right after taking the atmospheric data, any changes that the instrument has can be taken out of that measurement. So it's a very, very stable measurement. So that record that we have by the 2015, 2020 timeframe, so right about now, we expect ozone to have recovered about halfway. And so we're going to go up there and we're going to see how that's going, what the pattern of recovery is. And then we'll be able to use that to compare with models to see whether or not we understand the reason it's recovering the way it is. Hopefully it's recovering very nicely. We'll know soon.